Welcome back to QHSE Talks. Today's episode is about a shift that's been quietly reshaping how safety professionals are expected to think, especially when it comes to design decisions that lock risk into a system long before anyone ever steps onto the job. When we analyze serious incidents, fatalities, disabling injuries, long-term occupational illnesses, the pattern is almost always the same. These events rarely begin with unsafe behavior. They begin with systems that were never designed to be forgiving, layouts that force exposure, equipment that assumes flawless human performance, processes that rely on procedures to control hazards that could have been engineered out entirely. For years, safety has tried to manage that reality after the fact. We build systems first, then layer on training, rules, signage, and PPE. And when those layers fail, the focus tends to land at the point of use, not at the point of design. Prevention through design challenges that entire model. It shifts safety upstream to the stage where decisions have the greatest influence and the lowest cost. It treats safety as a design constraint, not a corrective action. And this perspective was recently reinforced by one of the most engaged voices in the QHSE Talks community, someone who consistently brings sharp insight to our discussions, who highlighted just how central prevention through design has become in the new CSP-11 blueprint. That observation matters because it reflects exactly where the profession is going. PTD is no longer a side topic. It's now embedded in standards, in certification expectations, and in how risk is expected to be managed across an entire system lifecycle. Now, to set expectations clearly, this episode is an overview. It's the foundation. We're not going to dive into every technique or tool today. This is the first episode in a PTD series designed to give you the structure and mental framework that everything else will build on. Because before you can apply PTD effectively, you need to understand the system behind it, the logic, the life cycle thinking, and the standard that formalize the approach. And that brings us to the backbone of today's discussion.
That would be the American National Standard, ANSI Z590.3.
Exactly.
And we've really synthesized everything for you. We've pulled from the initial 2011 standard, its 2016 reaffirmation, and most importantly, the significant, much more holistic 2021 revision.
So our mission today is to give you a complete, structured understanding of not just the why, but really the detailed how. How do you design these hazards completely out of the workplace?
And the core rationale, the guiding principle behind this massive organizational shift, it comes straight from the top, from NEO, the National Institute for Occupational Safety and Health.
What do they say?
They state it very clearly. One of the best ways to prevent and control occupational injuries, illnesses, and fatalities is to design out and minimize hazards and risks early in the design process.
It's such an elegant concept. It sounds so simple, but I imagine the implementation requires a ton of rigor.
It requires rigor, and it requires real organizational will. Look, when we commit to applying PTD concepts, we're aiming for three major interconnected goals. The first one, and this is probably the most important for systemic improvement, is achieving acceptable risk levels.
Acceptable risk levels.
Across the organization's entire portfolio. It's about being deliberate, in defining what risk you will, and just as importantly, what risk you will not accept.
Okay, so that's goal one. Goal two, and I think this is the one everyone understands instinctively, is the humanitarian component.
Absolutely. Preventing or, drastically reducing occupationally related injuries, illnesses, and fatalities. It's simple, really. If the hazard is successfully eliminated in the design phase, the worker just done. They cannot be harmed by it.
That's a massive leap beyond just relying on workers to always follow procedures or, always wear their gear perfectly.
It is. But the third goal is often the one that secures buy-in from the C-suite, and that is the reduction of cost.
The money.
The money. Specifically, reducing the often catastrophic cost of retrofitting that becomes necessary to mitigate hazards that just weren't sufficiently addressed during the initial design.
I think we've all seen that moment. The construction is done, the shiny new machine is installed on the floor, and then suddenly someone realizes the maintenance platform requires a worker to stand on a 6-foot ladder precariously balanced over a moving conveyor belt.
Right.
And that means an expensive, completely unplanned retrofit, which often costs, 10 times what it would have if it had been included in the original blueprint?
At least. It's what we call the cost multiplier effect. Research consistently shows that a design change made during the conceptual phase costs maybe a few $100s and a signature on a document. That exact same change, if you try to implement it after commissioning, might involve shutting down operations, hiring external contractors, and spending hundreds of thousands, if not millions of dollars. PtD makes the fundamental economic case for safety being an investment, not an expense.
Okay, let's unpack this history a bit then. Because for a standard that feels so relevant and, so modern, the idea has actually been percolating in the safety world for decades. Where do the formal roots of PtD really lie?
The initial push, the real momentum in the safety community, it started way back in 1994. The American Society of Safety Professionals, which was known as AS back then, they released a really foundational position paper.
And what was the gist of it?
It was all about promoting designing for safety concepts. This wasn't just about, general principles. It was a direct call to action, urging designers and engineers to actively, consciously consider the end user's safety and health in their work.
So the safety community was advocating for this for years. What was the tipping point that turned it from a position paper into, a major national movement?
That momentum really solidified in the late 1990s and early 2000s. You started to see a critical mass building across different sectors, manufacturing, construction, system safety experts. They were all kind of coming to the same conclusion.
Which was?
That the existing reactive safety models, the fix-it-after-it-breaks models, had hit their limit. They realized that incremental improvements in, say, training or enforcement just couldn't fix a fundamentally flawed design. You can't train your way out of a bad design.
And that strategic conclusion, that realization, must have paved the way for the major organizational driver in the U.S.
Yes, that led directly to the National Institute for Occupational Safety and Health, NIH, in 2007. They established the Prevention Through Design National Initiative.
So NIH gets involved. What did that change?
It changed everything. The NIH recognized that without a concerted national effort backed by serious research and resources, safety design would just remain sporadic and inconsistent from company to company. This initiative provided the institutional muscle the concept desperately needed to become mainstream.
And I assume that institutional backing inevitably leads to standardization. You need a clear, common language for everyone to use when they're trying to implement this.
Precisely. The NIH focus spurred the entire industry to develop a formal standard. This started with what's called a technical report, as CAC 797.001 back in 2009.
Okay, a technical report.
And that report essentially laid the groundwork. It was the precursor to the eventual ANSI Z590.3 standard, which was first published in 2011. And this standard isn't theoretical, it's the formal rulebook. It defines the roles, the responsibilities, the systematic processes.
And the standard continues to evolve. We mentioned the 2021 revision at the top. What was the real significance of that update? Why was it so important?
The 2021 revision was absolutely critical because it aligned the PPD standard even more closely with modern systematic risk management principles. And it also harmonized it with other global standards, like ISO 4501.
So it became more integrated.
Way more. It dramatically enhanced the guidance on risk assessment techniques, which we'll get into. It strengthened the focus on human factors engineering, and it made the connection between design safety and an overall occupational health and safety management system, or OHSMS, explicit. It wasn't just a suggestion anymore.
So Z590.3 is the definitive guide. But what's the scope here? Is PtD just about that initial moment of design and construction?
No. And this is a really key point where PtD differs from some of the earlier, narrower concepts of designing for safety. PtD is defined by its comprehensive scope over the entire life cycle of a facility, a process, or a product.
The entire life cycle.
Its entire life cycle. This means the standard applies across the board, from conceptual design and construction, through its daily operation and maintenance, and extending all the way to its ultimate disposal or reuse. It's cradle to grave.
It's a continuous obligation then, not just a one-time sign-off at the beginning. The standard breaks this down into a few key life stages, but let's focus on the three most relevant for hazard management. Let's start with the pre-operational stage. You call this the golden stage. Why?
I call it that because this stage The initial planning, the detailed design, the specification writing, prototyping, construction planning, this is where your design flexibility is at its absolute greatest. The opportunities for what we'll discuss later, risk avoidance, elimination, or substitution, are at their maximum. And crucially, the associated cost for making a change are at their absolute minimum.
Right.
If you can eliminate a hazard here on paper, it never even enters your system. A design review meeting is the cheapest and most effective way to eliminate risk, period.
But inevitably, some hazards are inherent to the operation, or they emerge unexpectedly over time. That moves us into the operational stage.
Right. The operational stage covers the system's daily use and all its ongoing maintenance. If hazards were missed in the initial design, or if operating conditions change, which, let's be honest, they always do, they have to be identified and evaluated.
And then what?
Then mitigation actions are taken through formalized redesign initiatives or adjustments to work methods. But the key is, this happens before any incident occurs. The watchword here is vigilance. You have to be constantly using tools like audits and inspections to catch those latent hidden conditions.
This is also the point where the absolute necessity of management of change, or MOC procedures, becomes immediately apparent, isn't it? If you don't manage the small changes, you slowly erode the integrity of the original PtD work.
That's a crucial early connection to make. You're absolutely right. Even during the operational stage, MOC is the mechanism that protects the design's safety integrity. If an operator decides to bypass an interlock for convenience, or the maintenance team substitutes a part with a non-certified component because it was cheaper or faster,
MOC should catch that.
MOC is designed to catch that. It ensures the system retains its acceptable risk profile throughout its entire working life. It's the gatekeeper.
And finally, there's the necessary but hopefully infrequent and reactive post-incident stage.
The post-incident stage is critical for continuous improvement. It involves rigorous investigation of incidents, near misses, and occupational exposures to determine the causal and contributing factors. Very often, these factors trace right back to weaknesses in the original design.
So this data becomes the feedback loop.
Exactly. It drives appropriate interventions, design modifications to achieve acceptable risk levels, and, just as importantly, it influences future designs. It ensures the same mistake is not repeated system-wide on the next project.
So we have this systematic lifecycle model. This whole framework sounds deeply integrated with general safety management practices. Does the Z590.3 standard officially position itself within that broader safety management system landscape?
It absolutely does, and this is one of the most powerful insights for any organization that's implementing PtD. Z590.3 is specifically designed to complement and provide the technical muscle for existing standards.
Such as?
Specifically, it aligns perfectly with the ANSI Z10 Occupational Health and Safety Management System standard.
The Z10 standard, for those who might be less familiar, that really outlines the overall framework, the commitment, the planning, the evaluation. It's the big picture.
Precisely. Z10 requires an organization to establish processes, to identify and take appropriate steps to prevent or otherwise control hazards and reduce risks associated with new processes or operations at the design stage. That's the mandate.
So Z10 says what you have to do.
In Z590.3, the PtD standard is the detailed step-by-step how-to guide. It provides the specific tools, the hierarchy of controls, the organizational roles, and the documentation requirements that you need to fulfill that Z10 commitment. It connects the philosophical commitment to practical, on-the-ground engineering.
Okay, let's move from that structural context to the organizational engine that has to drive this. This standard makes it very clear that PtD is not a suggestion. It's a mandatory management system component. Section 2, which deals with organizational requirements, is full of the word shall.
Yes, and that's not by accident.
So let's look at the absolute non-negotiables for top management. What do they have to do?
The standard is unequivocal about leadership's role. First, top management shall communicate and make it crystal clear to every single person in the organization, from the engineers to the procurement team to the subcontractors on site, that the overarching goal of this entire risk assessment process is to achieve acceptable risk levels.
And that has to start at the very beginning.
It has to start at the conceptual design phase, where your initial safety goals are set concurrently with all the other project objectives, like budget and schedule.
Which means safety can't be balanced against cost or schedule later in the project. It has to be treated as a primary, non-negotiable objective from day one.
Precisely. If management frames safety as some kind of optional add-on, it will be the very first thing that gets dropped when the project is under pressure. The visibility of this commitment from the top is everything.
And visibility requires specific accountability. The standard dictates the creation of a pretty key role to ensure this happens.
It does. That's the second major shall requirement. Top management shall designate a project design review manager, or PDRM. Yes, and this individual is the linchpin of the entire process. Their job is highly technical and, frankly, often highly political. They are responsible for developing and updating the design hazard assessment process, for facilitating those critical review sessions, and for making sure all the documentation is rigorously maintained.
That sounds like a really powerful position. But what ensures this PDRM isn't just sidelined or overruled by, say, the engineering or finance department who are worried about deadlines and budgets?
The reporting structure is the key to their authority. The standard specifies that the PDRM reports directly to the executive or the group with overall project management responsibilities.
So they have a direct line to the top.
A direct line. This ensures that the PDRM has the necessary clout to actually influence design decisions before they become fixed costs, before the concrete is poured. They need to have the authority to stop a design, or at least to escalate a safety deviation, without any fear of retaliation from mid-level project managers who are focused solely on deadlines.
That organizational structure is really the defense against what you might call design drift, where good intentions get watered down over time.
Absolutely. And to solidify that, the standard states that design professionals shall not deviate from established safety standards unless that deviation has been explicitly approved and documented by top management or the designated PDRM.
So no unilateral decisions.
Exactly.
Yeah.
This prevents engineers from making, on-the-fly decisions that might bypass the safety review process, even with good intentions.
Now let's talk about the data, the information that informs the PDRM and the design team. The standard really stresses the critical importance of valuing employee knowledge.
This is such a practical and often overlooked point. It's a recognition that the person wearing the uniform, the person on the floor, is often the greatest expert on how a system actually fails in practice, not just in theory. The effectiveness of your hazard identification and risk assessment improves dramatically when you utilize the knowledge, the skills, the experience, and sometimes, frankly, the frustration of the employees who are closest to the hazards every single day.
So the designer might draw a perfect, compliant maintenance walkway on a CAD model. But the maintenance worker is the one who knows that access panel is actually impossible to reach when the plant is running at full temperature and they're holding a heavy wrench in their hand.
That is the perfect example. Management must establish a culture where this collaboration is not just allowed, but valued and respected. This isn't just about putting up a suggestion box. It's about making frontline workers integral participants in the design and redesign activities. They possess this contextual, tacit knowledge about operational anomalies and failure modes that no checklist or historical database can ever fully capture.
Okay, let's pivot to the supply chain. This is arguably one of the most common entry points for unassessed hazards into a workplace. How does PtD enforce safety requirements on external partners, on suppliers?
This is where procurement becomes a critical control point. The whole goal is to avoid importing hazards and their associated risks into your workplace. So when you're considering new equipment, new processes, new materials, top management shall establish and document the occupational hazard and risk design specifications and objectives right up front.
What should those design specifications actually look like in the contract language? I mean, you can't just write, make it safe.
No, you have to be explicit and measurable. For instance, your contract might mandate things like specific failure rate targets, like mean time between failures or MTBF.
Okay.
It could require certain isolation points, like all energy sources must be lockout to gout, capable from floor level, no ladders needed. It could specify a maximum noise output, say 80 dBA, or specific materials limitations, like no known carcinogens unless the process is fully enclosed. Detailed discussion points covering construction, expected use, and service must be put in writing with that supplier.
So the purchase order isn't just about cost and delivery date anymore. It becomes an enforceable safety document.
It absolutely is. Procurement documents shall include safety and health performance specifications. And furthermore, Z590.3 shifts the initial burden of proof onto the supplier.
How so?
The supplier must provide documentation certifying that a risk assessment has already been conducted on their equipment. And that documentation has to prove that the residual risk achieves the acceptable level that you, the procuring organization, specified for all reasonably foreseeable uses.
That's a game changer. It forces the manufacturer to apply PtD principles themselves, rather than making the buyer fix all their flaws after the fact. But, documentation can be faked or superficial. How does the procuring organization validate the supplier's claims?
You're right. You can't just trust the paper. Validation is done through rigorous inspection and test protocols which management shall develop. And this isn't just one step. It's a multi-phase verification process designed to catch issues as early as possible.
Okay, walk us through those phases of validation. What's the first one?
Phase 1 is the factory acceptance test, or FAT. If it's at all practicable, the organization's team, so the PDRM, maybe a maintenance tech and operator, they should visit the supplier site before the equipment ever ships.
And what are they doing there?
They're witnessing a test run of the equipment according to pre-described criteria, focusing specifically on safety functions. Are the emergency stops working? Do the interlocks function as designed? You find the problems in their house, not yours.
Phase 2 is after the equipment arrives on site.
Right. Phase 2 is the site acceptance test, or SAT, and commissioning. After the equipment is installed in its new home, the team conducts a much more comprehensive test. They're trying to assure that the acceptable risk levels are achieved in the new environment during startup, operation, changeover, and maintenance. This is where you test things like, is the ventilation effective enough in this room, or does it comply with our local electrical codes?
And the third and final phase?
The third phase is the final sign-off. This often involves a formal operational readiness review. Management, operations, maintenance, safety staff, they all sign off that the equipment not only performs its intended function, but that it also meets all the safety requirements before production begins. This multi-layered verification ensures that the paper claims are validated by physical performance under realistic operating conditions.
All right, now we get to the brass tacks, the systematic process for actually achieving that acceptable risk level. The Z590.3 standard lays out 11 distinct elements of hazard analysis and risk assessment that management shall apply. This isn't just a guide, you called it a structured choreography for risk reduction.
It is the structure, absolutely. And what's so critical here is that this 11-step process isn't a one-time event you do at the beginning. It's a continuous, cyclical assessment that you repeat at critical junctures throughout the design and the entire life cycle of the system. Let's take our time and walk through these elements one by one.
Okay, start at the absolute beginning, the tool set. Step 1, select a risk assessment matrix. Before you do anything else, an organization shall create and gain agreement on a suitable matrix or some kind of qualitative scoring system.
Why is that so important to do first?
Because this matrix is essential for creating a common language for communicating risk. It's how you categorize the combinations of severity, the S, and probability, the P, into standardized risk levels, high, moderate, low. You have to ensure this matrix is suitable for the complexity of your operations. Without it, one person's high risk is another's moderate.
Once that tool is chosen and agreed upon, we have to define the scope of the work.
That's step 2, establish analysis parameters. This is a deceptively simple, but a very frequently missed step. You must clearly define the boundaries of the system, the process, or the equipment that you're analyzing.
And that includes all the different ways it operates.
All of them. This includes defining all operating phases: construction, startup, standard operation, maintenance, emergency shutdowns, cleaning, and eventual disposal. A very common pitfall here is failing to assess the non-routine phases, like maintenance or cleaning, which statistically are often the most hazardous.
The design team focuses on the perfect, normal operation. The safety team has to focus on the imperfect, abnormal operation.
Exactly. Step 3 is then the core discovery phase. Identify hazards. Now you can start identifying every potential source of harm. This uses a mix of techniques. You're reviewing system specifications, you're consulting historical data like incident reports from your own company and the wider industry, you're checking against codes and regulations, and you're interviewing the intended users.
What are you specifically looking for?
Crucially, you must consider failure modes, human error potential, and the potential for unwanted energy releases. That's the big one. Thermal, electrical, kinetic, or stored pressure. These are the primary drivers of severe incidents.
Okay, step 4 is where we start to quantify the potential damage. Assess severity of consequences.
Here, we establish the probable degree of harm or damage that can result from that hazard. And the standard is very clear on its limitation here. We focus on the worst credible consequences, not the worst conceivable consequences.
That's a really important distinction, credible versus conceivable.
It's vital. Focusing on credible scenarios prevents what we sometimes call paralysis by analysis. We don't spend months modeling a simultaneous quadruple catastrophic failure that has a probability of 1 in 10 billion. We focus on realistic, high-impact events. A valve failure leading to a major chemical leak, a guard failure resulting in an amputation. Those are credible.
That keeps the assessment grounded and, more importantly, actionable. Step 5 then brings in the likelihood.
Exactly. Determine occurrence probability. Now, we estimate the likelihood of that specific hazardous event or exposure actually occurring. For brand new equipment, this is often a qualitative judgment. Is it rare, likely, frequent? Based on industry experience and the known reliability of the components. For existing systems, you might have quantitative failure data you can use.
So, with severity and probability now in hand, we execute step 6.
Define initial risk. You take your S and your P, and you use the matrix from step 1 to categorize the risk level. This initial rating, high, serious, moderate, that's your baseline. If it comes out as high, the standard demands immediate, high-priority intervention. This step clearly establishes the gap between the current design and your desired acceptable risk level.
And step 7 is the action phase, applying the controls to close that gap.
Right. Select and implement controls. This is where we bring in the hierarchy of controls, which we'll dive into in detail later.
Yeah.
You must select and implement the most effective controls available, starting with avoidance, elimination, substitution, and engineering controls to reduce that initial risk level down to one that is acceptable.
After the action is taken, we move into validation.
Steps 8 and 9 are all about accountability. Step 8 is assess the residual risk. So after the controls are in place, you reevaluate the risk level. How much risk is left? Is it still moderate? Did it go down to low?
And then you have to decide if that's good enough.
That's step 9. Risk acceptance decision-making. A formal decision is made by management. Is this residual risk acceptable according to the organization's predefined criteria? If it's still too high, you go back to step 7 and you implement further controls. You keep iterating.
This decision-making step, step 9, that can be fraught with political difficulty within an organization, can't it?
It absolutely can. The PDRM and the safety team might recommend a costly engineering control because it's most effective. But management might opt for a cheaper administrative control. If they do, they must formally sign off on accepting that higher residual risk. That decision requires documentation and often some very tough conversations about the true cost of human safety versus capital expenditure.
And finally, you have to close the loop.
Step 10, document the results. This includes maintaining comprehensive records of the entire analysis, the controls that were implemented, and that final acceptance decision. Step 11 is follow up on actions taken. You track the actions to provide for continuous improvement. This ensures that the controls were implemented correctly in the first place and that they remain effective over time, which fulfills that long-term OHSMS requirement.
That is a powerful, systematic process. Now let's look at the actual techniques that you would use within those steps. The standard acknowledges there are a massive number of techniques out there, but it suggests that proficiency in 3 key concepts is usually sufficient for most projects.
That's right. The field is huge, but if you have a good handle on these 3, you're in great shape. The 3 core techniques are preliminary hazard analysis, or PHA.
Okay.
What-if checklist analysis, and failure mode and effects analysis, which is known as FMEA.
So starting with PHA, that clearly belongs in the very early conceptual phase of a project.
It's a fundamental system safety technique, you're right. It is used in the very early stages of design, the concepts and initial definition phase, to identify and broadly evaluate hazards. Because the design details are minimal at this point, a PHA looks at system components and energy sources in a general way. High-pressure systems, electrical power, moving parts. It assesses the risk based on these general categories. It's excellent for scoping the project and prioritizing areas that will need a more detailed analysis later on.
The what-if checklist analysis seems like it would be the easiest to execute, but potentially the riskiest if not done well.
That's a fair assessment. The what-if analysis uses structured brainstorming. You get a cross-functional team in a room, and you ask scenarios like, what if the power fails while the operator is inside the enclosure? Or what if the wrong chemical is loaded into this tank?
And that's often combined with a checklist.
Yes. Very often you'll use a checklist that's been adapted from industry best practices or regulatory requirements. Its main advantage is that it's cost-effective and relatively quick to do. However, the caveat is severe. Its quality is entirely dependent on the experience of the participants and the completeness of that checklist. If the designers in the room miss a what-if scenario, the analysis completely misses the hazard.
And then there's FMEA failure mode and effects analysis. That feels like the deepest technical dive into the hardware itself.
FMEA is the technique that is often preferred by design engineers because it's very systematic. It's a bottom-up approach used to evaluate how individual equipment fails and what the system's corresponding response will be.
Can you give an example?
Sure. For a pump, a failure mode might be motor ceases. The effect of that failure might be process halts and upstream pressure builds to a dangerous level. The existing safeguard might be a pressure relief valve, and the necessary action might be replace the pump with a model that's rated for a higher operating temperature to prevent seizing. It generates these qualitative systematic lists that are superb for assessing single-point vulnerabilities in a system.
The source also highlighted another one, fault tree analysis, or FTA. Where does that methodology fit in relation to FEA?
FTA is complementary but distinct. Where FMEA works bottom-up, starting with a single component failure and seeing where it leads, FTA works top-down.
Top-down.
You start with the undesirable high-severity event, the top event, for example, explosion of reactor A, and then you deductively trace all the combinations of component failures and human errors that could possibly lead to that event. You build a logic tree underneath it.
So when would you use that? It sounds very complex.
It is. FTA is best suited for analyzing highly redundant or highly complex high-energy systems. Think nuclear reactors or critical aerospace control systems, where multiple simultaneous failures are required to cause a catastrophe. For most industrial systems, an FMEA or a what-if analysis is usually sufficient, but FTA gives you that quantified, deep analysis of complex interdependencies when the stakes are incredibly high.
Okay, so if the 11 steps are the choreography, then the hierarchy of controls is the definitive marching order. This is the core principle of PTD, and Z590.3 frames it very specifically as the hierarchy of risk treatments. The prioritization rationale here seems critical.
The prioritization is everything. We have to emphasize that the hierarchy is sequential and it is ranked by effectiveness. The top 4 levels, avoidance, elimination, substitution, and engineering controls, are inherently superior to the others.
And why is that?
Because they are preventive actions. They prevent the hazardous energy from interacting with the worker in the first place. They rely minimally on human behavior or compliance, and they are very difficult to bypass or defeat.
That really is the philosophical shift, isn't it? Moving safety control from the unpredictable human element to the predictable, reliable engineering element. Let's go through all 7 levels in detail, starting with the most preferred, level 1, which I imagine is often the most challenging concept for organizations that are used to retrofitting.
Level 1. Risk avoidance.
Yeah.
This is the most preferred. And it's somewhat unique to PTD because it occurs before the design is even committed to paper. Avoidance means preventing the entry of hazards into the workplace during that initial design concept phase. You are using the blank sheet of paper opportunity to steer clear of high-risk scenarios entirely.
Can you give some tangible examples of what avoidance criteria would look like in a specification document for a new project?
Absolutely. Think about setting mandatory performance criteria that just rule out known hazards from the start. For noise, you might specify. All newly procured equipment shall be designed to achieve a maximum sustained noise level of 80 dBA at the operator station, period.
So you avoid the hearing loss hazard and the need for a hearing conservation program and PPE right from the get-go.
Exactly. For a chemical process, you might specify. Any process requiring Category 1 hazardous chemicals must be conducted solely in a closed hard-pipe system with no open-air sampling ports. That avoids environmental release and worker exposure hazards. For structural design, you could specify, design the roof HVAC system to incorporate external maintenance access walkways rather than requiring internal confined space entry. You've avoided the confined space hazard completely.
So avoidance is all about preemptive choice, ruling out the hazard before it even becomes a design problem you have to solve.
That's it. Now, if we cannot avoid it in the concept phase, the next best thing, level 2, is elimination. Elimination is the removal, the purging, or the taking away of risks that are already discovered in existing designs or operational modes. So if you realize your current process requires workers to manually lift 50-pound sacks repeatedly all day, an active elimination might be redesigning the process to use bulk tanker delivery and an automated pumping system. You've eliminated the manual lifting hazard entirely. Another example is eliminating a fall hazard by designing a piece of equipment so that all the lubrication and service points are reachable from the floor, thereby eliminating the need for working at height.
That sounds incredibly similar to avoidance. What is the practical difference in application between those two? They feel very close.
They are close, But the timing is the key difference. Avoidance is a decision made on paper before any real design work starts. It's a constraint you set for the designers. Elimination is typically a redesign effort once a system or a hazard has been identified. It's often applied during the operational phase, or maybe when you're reviewing a prototype. So avoidance is purely preventative. Elimination is corrective design.
Okay, that clarifies it. Level 3, substitution. This is about trading a major hazard for a lesser one.
Right. Substitution involves reducing risks by replacing a hazardous method or a hazardous material with a less hazardous one. The classic example is with solvents. If you use a highly flammable solvent with a low flash point for cleaning parts, substitution might involve replacing it with a water-based or a non-flammable cleaning agent.
And in other areas.
In energy systems, you might replace a huge high-voltage motor control center with a series of smaller, lower-voltage servo systems. That dramatically reduces the potential arc flash hazard. The key is that a hazard is still present, but the severity or the probability of harm is greatly reduced.
So these first 3 levels are all about preventing the hazard or making it significantly less dangerous. Level 4 is the last line of defense before we start relying on human behavior. This is engineering controls.
Engineering controls incorporate physical safety devices to prevent access to the hazard or to physically separate the worker from the hazardous energy. And the Z590.3 standard makes a crucial distinction here. We must prioritize passive controls over active controls.
Explain that distinction. What's the difference between a passive and an active engineering control?
Passive controls are generally simpler, more reliable, and much less defeatable because they do not rely on sensing technology or energy input to function. They just work. Examples are fixed machine guards, robust enclosures, solid guardrails, permanent ventilation systems, or structural fall prevention systems that are installed directly into the building.
And active controls.
Active controls, things like presence sensing devices, safety light curtains, or pressure mats, they require complex logic. They need power, calibration, and regular maintenance. They're designed to stop the hazard when a certain condition is met. Passive controls are preferred because they stop the hazard always.
So machine guards, interlocks, circuit breakers, and soundproof enclosures are the absolute staples of engineering controls.
They are. They're the physical realization of the design safety choices that were made. And once we move below level 4 on the hierarchy, we are now relying on communication, training, and compliance.
Which brings us to level 5, warning.
This is where we attempt to mitigate risk by alerting the worker. Warnings provide notification systems, things like startup alarms, strobe lights, critical signage, or visual indicators that a hazard is present or is about to become present. They inform, but they do not physically prevent access. They are meant to supplement engineering controls. They are never a substitute for them.
Level 6, administrative controls, is basically relying on the rules of the road.
That's a good way to put it. Administrative controls rely on the organization of work itself. This means things like training, written procedures, direct supervision, job rotation to limit exposure, scheduled rest breaks to prevent fatigue, and the mandatory use of management of change protocols. The standard is very pragmatic here, noting that achieving a superior level of effectiveness in these methods is intrinsically difficult.
Why?
Because they rely entirely on consistent human performance and supervision. They are easily circumvented or just forgotten under production pressure.
And finally, the last line of defense, the least preferred option, level 7, personal protective equipment, or PPE.
PPE reduces the impact of a hazard on the employee, but it's always the least preferred option. It fails if it's damaged. It fails if it's not worn correctly. It fails if it's the wrong type of equipment for the hazard. If a designer is relying on the worker wearing hearing protection or a respirator, it means they failed to engineer the hazard, the noise, or the airborne contaminant out of the system in the first 4 more effective steps. The design goal should always be to reduce the reliance on PPE to a practical minimum.
As you noted earlier, the 2021 revision of Z590.3 significantly enhanced the guidance on integrating human factors in prevention through ergonomics, or PTE. This shift seems to acknowledge that poor design doesn't just cause acute sudden accidents. It systematically injures workers over time through repetitive strain.
The case for focusing on PTE is, frankly, overwhelming. When we look at the occupational injury data, ergonomic-related risks, which lead primarily to work-related musculoskeletal disorders or WMSDs, account for a full 33% of all disabling occupational injuries.
A third of them.
A third. But the financial impact is even more dramatic. WMSDs account for more than 40% of the total workers' compensation costs across most industries in the U.S. That is a massive, massive operational drain that PTD is uniquely positioned to fix at the source.
And it goes beyond just WMSDs. If a system is illogically designed, if the controls are confusing, it facilitates dangerous mistakes.
Absolutely. Systems that ignore fundamental human factors principles create what we call error-prone or error-causing situations. Poor interface design, confusing controls, inaccessible maintenance points, inadequate or outdated documentation. All of these things introduce complexity that leads to both minor and major errors, which contribute significantly to fatalities and serious injuries. We have to design systems assuming human beings are fallible and will, eventually, make a mistake under pressure.
So how does Z590.3 define this discipline, human factors engineering, in the context of design?
Human factors engineering is defined as the scientific discipline concerned with understanding the interactions among humans and other elements of a system. It applies theory, principles, data, and methods to the design process in order to optimize human well-being and overall system performance. The entire point is to make the system fit the human, not force the human to try and fit the system.
And to design systems that minimize error, we first have to understand the mechanisms of human error. You mentioned Rasmussen's classification, which the standard references. Let's explore those core categories of error.
Rasmussen classifies errors into two main categories: execution failures and planning failures. So let's start with execution failures. These occur when the intended action was actually the correct one, but it was carried out incorrectly.
And these execution failures break down further into slips and lapses.
Right. A slip is a failure of execution that's related to an observable action. You intend to push button A, but you accidentally push button B because they look identical and they're mounted too close together on the control panel. This is often a failure of attention or perception, and it's easily mitigated by better design, color coding, spacing, using different shapes or sizes for critical controls.
And a lapse.
A lapse involves a memory failure. You forget a critical step in a well-known sequence, maybe because you were interrupted. This can be mitigated by design, too, by using mandatory interlocks that prevent the next step from happening, or procedural prompts that are built right into the system's interface.
So those are the unintended actions. The second major category is planning failures, what Rasmussen calls mistakes.
Planning failures, or mistakes, are much more complex because they involve a cognitive misjudgment. In this case, the intended action is carried out correctly, but the action itself was inappropriate for the situation.
Can you give an example of that?
Sure. If you follow an incorrect maintenance procedure because the documentation was outdated or misleading, that is a rule-based mistake. You followed the rule, but the rule was wrong. If the error comes from deficiencies in your judgmental or inferential processes, say you misdiagnosed a system fault because the gauges were confusing or poorly laid out, that's a knowledge-based mistake.
What's so fascinating here is that the PtD approach seeks to fix the design that allows or encourages that mistake to happen in the first place, whether it's a physical slip or a cognitive error.
Precisely. We address slips and lapses through physical engineering controls like better guarding or unique interfaces. We address rule-based mistakes by designing systems that are more intuitive and self-correcting, and by ensuring our MOC procedures keep all documentation accurate. The 2021 Z590.3 update made it mandatory to integrate PTE into all aspects of the design process, including the detailed design reviews and even the procurement specifications.
Let's look at that crucial financial and practical application of PTE by using the case study that was provided in the source material. The implementation of the Ergonomics Risk Assessment Tool, or ERAT. What was the initial high-risk scenario they were facing?
The initial hazard was a manual packaging operation in a warehouse setting. Workers were repetitively bending, twisting, and lifting small 5-pound boxes and fitting 4 of them into a larger shipping container for several hours a day. It sounds minor, but the sheer repetition and the sustained awkward postures created a massive cumulative trauma risk for WMSDs.
And the ERAT tool was used to quantify that risk.
Right. The ERAT is a very efficient, simple checklist that's used to score various risk factors: repetition rate, the force applied, carrying distance, awkward postures, environmental factors, all relative to the duration of the task. When they applied it to this manual operation, the risk assessment categorized it as high risk. It fell into what's called Action Level 3, which mandates immediate, urgent intervention and redesign.
So what was the PTD treatment that was selected to reduce that high-risk level?
The treatment proposed was full automation of the packaging process. This included robotic handling, automatic box forming, filling, and sealing. In terms of our hierarchy of controls, this is the highest possible level you can achieve. It's a clear act of both elimination and avoidance.
Right.
They completely eliminated the manual repetition, the lifting, the awkward postures, and therefore the associated WMSD risk.
Automation like that, though, is a massive capital outlay. For an organization to commit, what was it, $750,000? The financial justification has to be absolutely rock solid. Did the post-treatment analysis actually hold up?
It did, emphatically. And this is the kind of data that safety professionals must be able to present to management. The post-treatment analysis showed a stunning 97% annual cost reduction.
97%.
And this reduction wasn't just a hypothetical number. It stemmed from the elimination of injury claims, reduced training needs for these high-turnover jobs, and minimized associated administrative costs. The automated system required an upfront investment of $755,000.
And what was the return on that significant capital investment? What was the payback period?
The analysis demonstrated that the cost savings resulted in a payback period of only 2.177 years. Less than 2.25 years to fully recoup the entire investment, just through avoided costs and increased productivity.
That is the ultimate proof that PTD is not a compliance cost. It is a business strategy that protects the balance sheet.
Absolutely. The case study proves that when you move safety to the conceptual design stage, when you apply these PTE principles, you unlock massive operational efficiency and financial returns. OHS professionals must become fluent in this language or ROI to secure the resources needed for these top-tier controls.
Finally, let's just revisit the concept of management of change, or MOC. We touched on it earlier, but in a complex, highly engineered system like that automated packer, why is MOC so vital throughout the entire life cycle?
MOC, which is detailed in the Addendum K of Z590.3, is the procedural guardian of the entire PTD effort. That system was designed to function safely under a very specific set of parameters. If an operator down the line replaces a standardized sensor with a cheaper, non-standard component, or if the maintenance team modifies the safety circuit logic to speed up diagnostics.
Or even if the organization just changes the raw material supplier using a slightly different box.
Precisely. Any of those changes could fundamentally undermine the engineering controls that were so carefully designed in. They could inadvertently reintroduce the exact hazards the design team spent months eliminating.
And MOC is the process to prevent that.
It is. MOC ensures that any modification to equipment, materials, processes, or even the organizational structure is formally evaluated for its potential impact on safety and health before it's implemented. It's the mechanism that maintains the integrity of the design throughout the operational life of the system. It prevents that well-designed, low-risk system from decaying back into a high-risk liability over time.
This has been an incredibly exhaustive, deep look into prevention through design. To just quickly recap the framework, PTD demands that organizations apply risk controls as early as humanly possible during the conceptual, pre-operational stage, where that design flexibility is highest and the costs for making a change are at their lowest.
And this application must strictly adhere to the hierarchy of controls. It has to sequentially move from the most preferred treatments, risk avoidance and elimination, and work its way downwards. The focus is always to proactively engineer safety into the system, which minimizes and ideally eliminates the reliance on less reliable human behavior, warnings, and personal protective equipment.
And organizationally, the commitment has to be mandatory. Top management must establish the goal of achieving acceptable risk levels. They have to empower a project design review manager with real executive authority. And critically, they have to integrate rigorous safety and health performance specifications into all procurement processes to ensure that hazards are not being imported from suppliers.
And finally, that integration of human factors and ergonomics, PTE, is absolutely essential for operational excellence. Designing to prevent WMSDs and minimizing the conditions that lead to human error, whether they're slips, lapses, or mistakes, translates directly into staggering financial gains, as we saw with that rapid 2-year payback on a major automation project.
It seems PTD really transforms safety from a reactive check-the-box exercise into a foundational approach for operational success. It demonstrably improves productivity, quality, company reputation, and financial health by preventing those catastrophic costs that come with retrofitting and workplace injuries.
The integration of that systematic 11-element risk assessment process and the PTD hierarchy allows organizations to fundamentally move past simply reacting to risk. They can start to proactively design safety, efficiency, and worker well-being into the very DNA of their operations. Now that you understand this rigorous, financially justifiable framework, the question for you is, where in your world, in your next project, can you start designing out hazards today?
That is a deep thought to chew on. Thanks for guiding us through the complexities and the strategic demands of ANSI Z590.3.
It was my pleasure.